Hope you have settled down and have a short break. This afternoon we have a panel discussion on revolutionary tools for science. The panelist members are Prof Aaron Ciechanover, Prof Didier Queloz, and Sir Konstantin Novoselov. Moderating the panel today will be Prof Gisbert Schneider, Director of the Singapore-ETH Centre, SEC. Please warmly welcome the panel and our moderator, and I'll hand the session over to Prof Schneider, please. Thank you.
Thank you very much. I'm happy, it's a pleasure to chair this special panel this afternoon on revolutionary tools for science. And as you will see in the future, I have found one particularly revolutionary tool, that is my glasses, because this way I can see you and that way I can see my notes. Let's kick it off right away with a statement. It's a general perception that new methods and tools are essential drivers of scientific breakthroughs. New methods and tools are essential drivers of scientific breakthroughs. Today, we want to explore this hypothesis. And with me, I have three fantastic panelists, revolutionaries in their own right. Aaron Ciechanover, a professor of biology, medicine. He won the Nobel Prize in 2004 for characterizing the method that cells use to degrade and recycle proteins using ubiquitin. Welcome. Next one is Professor Didier Queloz. He was awarded the Nobel Prize in Physics in 2019 for the discovery of an exoplanet orbiting a solar-type star. And next to me, Sir Konstantin Novoselov. His work on graphene earned him the Nobel Prize in Physics in 2010. So we have a diverse group of panelists here with me, and they all work with various kinds of tools and technologies, be it large-scale facilities or very small-scale tools in their daily work and laboratories. And we will explore to which degree these tools are essential for scientific breakthroughs and how to define and identify new revolutionary tools for science of the future. Now, but first I would like to ask all three of you to briefly introduce your field of research and maybe mention one or two tools that have been essential for your seminal findings in the past. And I'd like to invite you, Aaron, to make a start. Please use the mic.
So my name is Aaron Ciechanover. I'm a physician by training. I graduated the Hebrew University of Jerusalem, then became a military physician because in Israel there is a mandatory military service, a combat physician, and then I did partial training in surgery, and then I decided that I don't want to practice medicine anymore, and I went to do a PhD with Avram Hershko. And during the PhD, we discovered the ubiquitin system, which is an intracellular proteolytic system. It degrades protein within cells, unlike proteins that are degraded like in the stomach or in the intestine outside of the cell. And this is mostly a quality control system that degrades denatured, mutated, and otherwise non-functional proteins. Finishing my PhD, I went to MIT for several years and did a postdoc with Harvey Lodish, where he was generous enough to let me work also on the ubiquitin system. So I continued my own studies on the ubiquitin system, and after a few years at MIT, I returned back to Israel, and I've been a faculty member in the Faculty of Medicine of the Technion, which is our Institute of Technology, ever since. Since we discovered the system in the late 70s, I'm very proud that we used what we call old good biochemistry. Lots of columns to purify proteins, to characterize them. And there was no molecular biology at the time. There was no cloning at the time. The human genome was not known. It was very, I wouldn't say primitive, but in retrospect, looking at it, I don't think that the ubiquitin system that contains close to 2,000 proteins, it's about almost 8% of the human genome, could have been discovered not using biochemistry. With genetics, you can discover one protein by screening for mutation, but you can never discover a cascade. It's a very complicated cascade in order to degrade a protein inside the cell because proteases are kind of destructive, and you cannot let them just float around. So you need first to signal the protein for degradation, so it will be recognized by an otherwise cryptic protease. So there is no way but to use classical biochemistry in order to purify it. But again, during the years, I have undergone myself, my laboratory, many revolutions. First was the revolution of molecular biology. We are cloning, we are mutating. Then was the revolution of using genetic manipulation of organisms, starting with Drosophila. Now we're working on models in mice, and so on and so forth. So things are developing very quickly in biology, and you have to adapt. And even the classical biochemistry has been now replaced because we are expressing all our proteins using molecular biological technology. So we have undergone major revolutions up to this point. But I think that my luck is that I'm commanding the two worlds, the modern world and the old one, so we can flip over whenever we need to use different methodologies. Now, the system is a very important system. There are basically, I don't know of any major cellular process that does not use the ubiquitin system. And many drugs have been developed based on it, mostly for cancer, but now people are moving, the pharma companies are all inside it, mostly for cancer, for blood, for leukemias. And now the world is moving to neurodegenerative diseases. Let it be Alzheimer, Parkinson, Huntington, polyQ expanded diseases, ALS, and so on and so forth, because these are all diseases of quality control. You might think of cancer, you have oncoproteins, proteins that cause cancer, that normally should have been removed but are not removed. Again, a malfunction of the ubiquitin system. In neurodegeneration, you might think of aggregated proteins that are disrupting the brain function or precipitating in the brain. Normally they should be removed, but unfortunately they are not being removed, and so on and so forth. So there are many diseases that we thought initially independently on them, but they can be rather gathered under a common umbrella of quality, protein quality control, PQC type of diseases, and the ubiquitin system is handling quality control in the cell, and hence misproper or improper function of the system leads to diseases, and the pharma company are walking in and developing drugs. So that's in a nutshell.
Thanks very much. Didier, what about your field of research?
Well, my field of research is astrophysics, so it's part of the physics, and it's a field when essentially we have to build anything we need, because you cannot really buy anything on the market here. Well, I happen to experience, using the very edge of technology to do an equipment for the discovery of the first planet. What we had as a challenge at that time is to develop a machine that would have the capability to make a specific measurements at an accuracy at that time that was never met. We're talking about building a spectra for stars and then computing from the spectra the actual speed or the radial velocity of the star. So the trick at that time, it was in the 90s, that we have been using is a series of new components that started to show up on the market, but were never really combined together and were never really considered for astronomy. One of them is optical fibers. It's something we all know and something we all use. There is not a single computer communication which is not done with this right now. Well, in the 90s, it was already kind of there, but they were not really specifically used for astronomy. The reason why is they were designed for working in the infrared or the short infrared, and in astronomy, the equipment we had were working in the visible light. And a new kind of fiber was available at that time. They were never ever properly being used for astronomy. So we had to develop with the whole team a way to have this fiber as part of the equipment, and that was critical because this fiber enabled us to reach a very stable entrance injection of the light into the machine. Then we built a new kind of spectrograph that was based on the old-fashioned design, but with a new component. But the real key here is on the market, something happened as well on the computer side. We had in the 90s a small PC. They were quite widespread at that time, but they cannot do proper scientific job. They were very limited. They had far less power than the cell phone we have right now, and you cannot really use it as an equipment to crunch number. To do that, you need big frame machine, and it means going back to the lab, getting access to big machine, using tapes. I'm still young enough not to having used, punching a card, but it was not very far from that time. No, what happened is there were a company called the Cray company. They used to build this massive supercomputer at that time, and they were based on a new architecture, which is 32 bits, which is something common these days. And part of the people of this company left the company and decided they could propose, instead of the big machine, also a smaller box with using this chip, the 32 Cray. This is known as the Spark system, Spark architecture. And in the 90s, they show up with a new machine, a new series called the Sun microsystem. And that was a revolution for astronomers. It was really literally a revolution, because you could have in your lab, next to your equipment, a machine that could do about the same that you would need for big equipment. This, combined with the hardware, combined with the optical fiber, was the breakthrough. Because by putting that together, we were able to produce a machine that reached the requirement in terms of precision, also treatment of the data. To give an idea, in these days, when you get a measurement of a star, to compute at the level we needed, that was quite sophisticated, the speed of the star, it was 1 hour of computing time. So when you have a couple of measurements during the night, if you want to make sure you compute the data before you start the next night, you need kind of a significant machinery to do that. And that was one of the use of technology. And I can bring plenty of other use on big frames, but that's one of the very specific use that I directly was part of it and benefited from the output.
Thank you very much. We'll touch on this topic again a bit later. Now to Konstantin. We've heard that methods are enablers in some way, one way or the other, revolutionary methods. And if I'm not mistaken, one of your first revolutionary tool, an enabler, was a piece of Scotch tape. Is that right?
Well, I guess it's just my teacher and colleague and friend Andre Geim just gave a talk in this audience, I guess, right? So probably I suspect that he did talk both about the frog experiments and the Scotch tape experiment. So but then when you say it in the just putting it in the past, unfortunately or fortunately, this trick is still quite active in our lab and actually in vast majority labs across the globe who work on graphene and other two-dimensional materials. So we can come back to this later. So my background is condensed matter physics. So I mainly studied mesoscopic phenomena in transport, in magnetization, in superconducting systems. Some time ago, we started to work with carbon materials, so graphene with the Scotch tape. Indeed, it was quite a change of topic for us. But then at the same time, we used the same technology, nanotechnology, to produce other interesting mesoscopic structures. So it's not only for to study electronic properties. I guess I'm not sure if Andre mentioned his frog story, but I'm sure that he mentioned the Gecko tape story, and then so Gecko tape is a product of the nanotechnology and the quite extensive use of the nanotechnological facilities as well. And these days, it's called so-called dry adhesives is quite a big direction for many chemical companies in the world. And but generally, as Kapitsa said, so Kapitsa is the guy who worked with Rutherford and then was stolen by Stalin into Soviet Union. He got his prize for the superfluid helium, And so he said 1 order of magnitudes in temperature, a new effect. So what we do in our labs, we just try to interrogate nature, and we try to put as harsh conditions as possible, as harsh interrogation techniques as possible. I'm sure we're going to be one day prosecuted by the Den Haag courts for this. What do we do with nature? But we just try to put it into lower temperature or higher temperature or high magnetic field. So my second attempt to get PhD, which also failed, was in the high magnetic field lab in Holland, in Nijmegen, and so generally, I guess we just need to figure out how do we make those interrogation more and more cruel. But in this process, the main tool is still your brain, I guess. That's and unfortunately, it's the tool which we still don't know how it works. So we just have to invent our own tricks how to make it working. We've been talking about the hardware tools quite a lot, and indeed, as I said, so new magnets, superconducting or resistive. We can go to lower temperatures, and commercially we can really lots of cryostats, types of cryostats are available now. But then there are also interesting tools in theory as well, right? When we talk about the description of our say something close to me in condensed matter physics, we describe metals or semiconductors. We used to describe it in terms of the electronic band theory, the valence band, the conductance band, the gap, the wave function of the electron. So the wave function, it doesn't exist, right? It's our tool. So we just use it as a tool, and maybe sometime later we'll figure out that some other description, some other language would be more useful. So these days we switch to more topological description of material. So it's a new tool as well.
Thanks very much for these first insights. And I'd like to bring up a first question from the online audience already, which fits very nicely in this first round of questions. What role can quantum technology play in the advancement of biology, medicine, physics, astrophysics, material sciences? Because you brought up theoretical tools in theory, as you call them, that can advance scientific breakthroughs. Quantum technology is somewhere at the interplay between hardware solutions and theoretical solutions. Maybe you could go on right away.
Well, okay, so I'm not really working on quantum computing myself. I do follow some of those experiments, and I'm sure that there might be some people in the audience who are much better than I am in the field. But I guess there are many different applications for the quantum computers these days. But one which, if we're talking about tooling, so one would be the quantum simulators, and usually, so if you get two-level system, so you can always try to simulate the Ising model, and you can arrange your systems, whether it's Rydberg atoms or cold or ions or Josephson junctions. You can arrange them with this specific interaction to mimic a particular geometry, square lattice, hexagonal lattice, whatever, and then many problems can be mapped in terms of equations on this Ising model, and then you can vary parameter, and you can get your quantum simulator. So I guess these days there have been some discoveries of the new quantum phases obtained through this method. It's still unclear whether it corresponds to anything in reality outside of that quantum system, but still it's quite interesting because it just shows you a variety of the quantum phases possible, macroscopic quantum phases with the macroscopic order parameters. So then it might serve as a guide towards what can we search for in terms of the new quantum states in the real materials.
Thanks very much. Aaron, if you had all the money in the world, what would be the tool you'd like to have, like to build?
Well, I think if I have to think back on the major technology that really revolutionized biology, is of course the discovery of the double helix. There is no doubt about it. I don't think that even Jim Watson and Francis Crick did understand at that time the full extent of the importance of their discovery, though they hinted it in a beautiful one-page Nature paper. So on the DNA basically lies the entire foundation of modern biology, and it ramifies to all directions. It was the beginning of decoding of the world of living organisms, from viruses to bacteria to plants to animals of all kingdoms and so on, understanding the code that make us what we are. It was the foundation to understanding mutations and diseases. It was the foundation of modern technologies like CRISPR-Cas, where we are now able to correct genes and to edit genes. We'll talk about bioethical issues that are related to it. It's not that simple. Modern drugs, understanding diseases, cancer, and so on and so forth. So, and now it ushers in this technology, I mean in big, a new era in medicine, which is probably the biggest revolution that medicine has undergone in its entire history, which we call the revolution of personalized medicine. So until now, until I would say maybe 20 years ago or even less, medicine was kind of a very primitive profession. It was a profession of one size fits all. If you had a tumor, we didn't understand the reason for the tumor, we couldn't analyze it, so we bombarded it with chemotherapy, with radiotherapy, with mutilated surgery. I myself, as a surgeon in the operating theater, witnessed it. And now we are able to look at different diseases, including cancer, in a very sharp pair of spectacles. We are able to understand exactly the mutation that leads to it, or the cascade of mutations. And we are able to treat these mutations with very sharp tools. So if you have a mutation, now you can model the protein. We don't need even structural biology anymore. The classical structural biology, we can use computers now. We can use AlphaFold and Meta, all this software that can predict at very low resolution structure of proteins, and then computational chemistry can fit in drugs, small molecules, in order to modulate the activity of those mutated proteins. So think about what this revolution, what this discovery of the double helix brought to us. And I think that whatever we are doing in the lab, whether we are generating a novel species of mice, of a mouse that have a disease, whether we are treating the mouse, whatever we are doing in the lab is relying all on this, and the revolution is keep on running, bringing more problems of ethics. Of course, we can devote some time to discuss it, but I think that modern biology relies at large on on a huge tree that stems from this small discovery made in Cambridge in the mid-50s.
Thanks very much. Before we go on, I have a number of requests from our online participants that we are encouraged to speak up. Apparently the volume online is a bit low. Maybe our technicians could take care of that. Thank you very much. Didier, the James Webb Telescope, is this something you use? Is this a revolutionary new tool?
Well, I think any tool that will be able to see something that was not visible before is a revolutionary tool. So it's a long history. It started with the Galileo telescope, 400 years ago. Yes, it's a new tool. Yes, it's a revolutionary tool. It's the first time there is such an equipment that we're using. It's not the only one. There are massive, big telescopes under constructions, also on the ground. We are developing the community, the biggest ever radio telescope in the world called SKA. So the number of this gigantic equipment always existed and will always exist. What I would like to do here is maybe to put that into perspective. I think to build such an equipment, it takes really a long time. There is about 30 years until the time when you think through this, when you assemble the technology. It's so long that usually you know that there is some piece of the technology you don't have. SKA is one example. SKA doesn't have the computer resource to just treat the data. It's not a problem because extrapolating about the power of the computer in 10 years, they will be in 10 years. So I say physics in the general and scientific in the general, when you have to do something of that scale, you have this time scale. I quite got asked about why would you do that? Should we not spend the money to do something else? On that, practically, when you see how much money it costs and how long you need to do it, it's very little. It's almost nothing, I think, what you spend in terms of development here. And you can compare this kind of big equipment. ISS is one of them, and you can do a long series of this magic special equipment. They're a bit like in Europe Middle Age, the cathedral. I think they are the pinnacle of the technologies, and they bring people together. They bring people together with a vision. They really want to do something which is new. 1,000 years ago, it was inspired by God. Right now, it's driven by this kind of strong impulse to understand and to see through, to see back in time, to see the beginning of the universe in the case of the James Webb Space Telescope. So there is a long series of such equipment. Another one, completely different, will be at the CERN when they're trying to understand the very intimate interior of the matter, also with similar kind of scale and similar time scale of development, and also some kind of global effort. I think I would like here to emphasize something that was mentioned many times during this meeting. This is not just not few people in the lab and playing, having fun here we're talking about. This is thousands of scientists that doesn't share the same language, culture, and country of birth, but they come together. They come together because they need to be together to do that. And I would like to mention something about what is the best equipment you may think about and related to that. I think there is something that to me is just amazing, and you mentioned it actually. This is the brain, and what makes us so special is these capabilities when you compare to the other alive animals or entities on Earth. Is this ability of the brain and to think through, to imagine, and to do something that we never thought would be possible. So if I would push what is the best machine, I think I would certainly look at the brain. And one way to make it, which would be very simple to improve, is I think we use little the mini brain we have on this Earth planet, and practically here. When you look at how many countries, how many people have really access to high educations to push the brain, it's a small fraction of what we could do. So if I would try to promote science, the best equipment, I would try to generalize access to educations all over the world for any continents. And until I have the same amount of people that is producing math coming from Africa than we do have from other continents, I think I would feel that we have failed here. So I think this is really what we have to promote. Anything we do on the top of that is just the creation of the brain. And that's unbelievable when you think that 10,000 years ago, we were, essentially fighting for food and for survival. And it's amazing right now we are 8 billion of inhabitants on this planet, and we kind of fix the problem of food. And it just seems so magical. So this would be my kind of take on this.
Yeah, can I check on you? So you just mentioned that you started those projects like SKA and web without even having the right tools, just hoping, projecting that it will be developed, but in particular in computing as well. And I know that astronomy relies quite a lot on the citizen projects.
Yeah.
Some of them, I participated in some. So, and in many of those citizen projects, you don't even need to use the brain, just use the few neural network layers like in your retina, and that's it. Do you see those students and citizens like me as the tool as well, as consumables and
That would be an amazing already citizen if you want to look at this. Yeah, definitely. You know, it's one of these many opportunities we have here, clearly. What is nice with technology is within a kind of horizon of 5 years, we can kind of guess a bit what to expect. What is impossible to guess is about, fundamental research. It's impossible to guess what is going to happen in 5 years because this is the unknown unknown. And while technology is something you build on something you know, so you're trying to push it until some extent until you reach some goal. So some of the development are being made with a perfectly clear idea in mind what technology is doing right now, and the idea in the labs right now how is going to be brought together to reach a new tools, to new equipment, which is a major difference between predicting the technology and predicting the new knowledge, because in that sense, new knowledge by definitions in something you don't know.
Absolutely. I'd like to encourage you again to speak more directly into the microphone for our online audience. Carol from somewhere in the world asked a question that is closely related to what you've just discussed. In your opinion, does technological advancement drive innovation, or do we need innovative ideas to develop revolutionary technologies?
I mean, first of all, we're talking about science here. So in terms of innovation, probably yes, but science is different from technology and from innovation. As Didier said, is the unknown unknown. So we basically what we do globally, and we just apply some pressure on a bubble, and we just hope that it will be, and we expand gradually the level of our knowledge. And then at a certain moment, this pressure bursts and bursts this bubble, and we expand into the new territory, and the new knowledge, the new concept appears, and then that's the scientific breakthrough, and it just defines a new frontier, and then a new knowledge pressure has to be applied. So the question is whether this burst happens because of the new tools. Well, I would say, of course, it has relevance, but usually, though, this burst and the new ideas is more a product of the collaborative research and deep thinking rather than one particular tool. So the tool produces data, and it keeps producing, and it's difficult to say which particular piece of data triggered this. So I would say that it's necessary, but it's not the crucial moment.
That is an interesting statement. Aaron, is this along your line of thinking?
I think that in biology, the answer is dual. Yes, innovation drives technology, and technology drives innovation. Because once you are this, I can bring you one example, again, from the world of DNA. Initially, people learned about the double helix. Then they wanted to understand how the information is embedded in the DNA. So they looked into sequencing. So they invented the way, like Dr Gisbert and others invented the sequencing of DNA. Then other technologies came. think about microscopy. You know, we used to use light microscopy, then came electron microscopy, and recently we wanted to understand the molecules, how they act in the live cells, so super resolution microscopy came in. So questions are driving technology, and the technology brings no questions. So I think it's kind of a cogwheel that is working in biology for sure. And the DNA, people say, okay, the DNA is making RNA, so let's go to RNA. So they invented methods in order to sequence RNA, but then came a more difficult technology, which is how to sequence proteins, because DNA and RNA are made basically of the same basis. But proteins are made of completely different components of amino acids. So then came proteomics, and so on and so forth, and post-translational modifications. So you see that, you know, one technology drives another question, the other question needs a new technology in order to resolve it, and so on and so forth. And I can bring you numerous other examples from the world of biology, how this is a kind of a cogwheel.
So I'd like to give the physics perspective of this,
Please do.
astrophysics. Okay, so I all agree with what has been said. From a physics point of view, there is something that we can absolutely say is technology is entirely, I said entirely driven by innovation. So this is where technologies sit. Well, the opposite is not true, actually. Innovation is not entirely driven by technology. It is in most of the case, but there are plenty of good examples. And my best example is Einstein sitting at his desk, thinking about beauty of time and space, and something doesn't fit exactly together into the physics which is known in these days. And he's coming with this beautiful theory, which is certainly one of the most beautiful theory that we have in physics, which is general relativity. Well, this is not driven at all by technology, except the technology of the pen and writing of the paper. But instead that, it's completely come out of his brain and with interacting with the rational thinking of the physics. But I can tell you this new invention, this idea, this physics pattern of the universe is completely used by the technology of your cell phone. It's called GPS. So it's one of the big examples where it doesn't go always in both directions.
Right. So just pouring money into a system to develop new technologies by very skilled engineers will not do the job.
Well, the most famous, I think, sentence, I don't know who started, I think Gilles de Gennes was one who said it, is you can spend all the money you want to try to increase technology, and the one I like to use is the steam engine. You use the steam engine, it's great, but you're never going to fly to the moon.
Let's come back to the question of the role of the human scientist, the human brain. Artificial intelligence is back. We have seen several waves of machine learning and AI throughout the past, say, 50 years. And we can expect that AI is back for good right now. It's here to stay. And there are several tools available belonging to the field of generative AI. Do you think these tools can support you in hypothesis formulation and actually coming up with ideas you have not thought of before? To which degree do you use machine learning or these deep learning tools for data analysis? Let's start that way. Konstantin.
Right. So it's absolutely clear that AI and machine learning increased our ability to do research and produce new data dramatically. So the beautiful example is the protein folding by AlphaFold, and I would say unfortunate example is the automated translation, which basically, for me, killed such a beautiful area of mathematics as linguistics. So, which personally I really regret a little bit, but okay, that's life. So that's how it works. So, but it is clearly an amazing tool, and I guess we really coming to the question which you and I should say that we use it in our work as well to do calculations on very complex structures which you won't be able to do, or you would need months and months on the most powerful supercomputer we have here in Singapore. So it's quite it is a beautiful tool, and it's if used properly, then it works and gives fantastic result. Now you've got your this beautiful question whether it can assist in hypothesis formulation and in hypothesis verification. That's it's still a big question for me. Say, I'm sure that in some cases where the number of possible hypotheses is limited, I think it will work. It will work really well. So, for example, if you are in medicine and you need to do the diagnosis, then you can probably formulate a hypothesis and then try to verify it and produce a series of tests required, which it needs to verify. Would it be able to recognize coronavirus back in 2010 through this? I don't know, because it is the production of the new knowledge. So for me, it's still an open question. However, say even a year ago, I would give a straight no to it. I'm so confident in the human brain that even though we don't understand it, but somehow magically it gives us the opportunity to produce discoveries and make the breakthroughs. I'm not so sure now that I would say it's not straight no. So it's no with some doubts that it probably can. There is some chance that it will be able to produce completely new hypotheses.
Aaron, Didier, do you concur with this conclusion?
Yeah, in medicine, AI is a very important tool, and I emphasize the word tool. Tools are developed by people. And so it's only a tool that helps us to advance knowledge. And in medicine, there are many ways that people are using now AI. We in the lab are using it for pathology. You know, pathology is still a profession of pathologists. They are using microscope in order to tell you whether there is cancer or whether there are processes. The advantage of AI is that we don't know what it's doing. We simply don't know. It gives us information about things that we have never thought of. You know, for example, you're looking at a cell. The pathologists look at some features, but the eye is limited and the brain is limited. But the AI can look at a zillion features at one time. So let's say that it can see a corrugated piece of a membrane that is like, and it's associated with a mutation. So it will point out to you that in this type of cancer, the mutation is associated with this corrugation. So now you can use a new biomarker in order to diagnose the disease. And if you follow the patient, it may give you a prognosis, a success of treatment, and so on and so forth. So the idea is that AI can see what we as people, our tools, cannot see. There is also a big movement of moving away from animal experiments in order to introduce new drugs to the market. There is a big public resistance to using animals, but on top of it, animals experiments are extremely slow. You can take, let's say that you need to screen 10,000 drugs. So how do you do it in animals? You're taking 10,000 mice and you inject the drug and you develop the cancer and you're following and you extract the tumor and you give it to the pathologist. It's an endless process. Therefore, development of a drug nowadays takes something between 5 to 10 years, costs billions of dollars, and the same for clinical trials. So what people are using now, they're using organs on chip. So you can make from stem cells a little liver or a little fatty tissue. Tiny, just a cluster of cells. And you can, with micro tubing, you can flow fluid via it, and then you can screen thousands of drugs at one time. And you can measure the output, what's going on. So you can measure toxicity, and you can do also side effects of potential drugs. And the only way to analyze it is by AI, because the output is huge in data. And again, the computer can combine all this data into a cohesive picture. And on the opposite side, you can develop drugs, not only monitoring toxicity. So you can take stem cells from patients, or you can take blood and convert it to stem cells and then go to any tissue you want, and you can develop personalized drugs. So again, you are doing these little organoids, and you are trying drugs that will fit the patient. And it's very easy to do because you are screening zillion of drugs in no time and almost with no, I wouldn't say with no money, but much cheaper. So AI is clearly going to accelerate in a big way and to lower the prices, to accelerate the development as far as time is concerned, to lower the prices dramatically, because an average drug now to bring to the market is something between 5 to 10 billion US, about.
Yeah, I think I would absolutely share. I think it's a tool. It's nothing else, nothing more. There's a bit of a buzz on this, but it's just a tool. Whether I'm using it, yes, every day. When I want to log in into my cell phone, it's just using AI anytime. It's a pattern recognition mechanism. Of course, I'm using it a lot in the translator. It's a fantastic translating machine. It's a pattern recognition system. So it's a tool that is based on a pattern recognition, whatever pattern means. It means you have a model, you match it closer to your expectations, and then it's something that you put together. No, there is nothing brilliant, there's nothing brainy, there is pretty much stupid, by the way. It's just pattern recognitions. But that's how I think it brings very impressive result, because it do it very fast. And it's possible because of the computer power. The idea of AI is very old, actually. And it has evolved because there's a lot of different mathematics way to do that. But since now the computer is so powerful, this is the most brutal, stupid use of a computer, which is trying to match all the possibilities with a kind of an optimization way and different filter, trying to reproduce what is going on in your brain. Well, I do think something else is going on in your brain, and we just touch the real pattern of what the brain is doing, the functioning of the brain. I don't think AI give us any clue about consciousness, and it would be nice, but I don't think it does. As a tool, it would certainly help my research. If I have zillions of data, I want to clean it up and get like a filter approach or simplify the data to be able to extract something out of it. But I doubt AI will write something really new. He may certainly reproduce plenty of fake papers, and there's a lot of games on that, I'm pretty sure. You can play with art, you can try to simulate many different pictures together, recreating something. This is fine. It's a tool, and nothing else, nothing more, and there will be more tools in the future that people will invent with the new technology available.
I can actually say why I'm less pessimistic, or whatever, not pessimistic, but skeptical than Didier. So generally, they say that a smart guy is someone who can make an analogy between two events, and a genius can make analogy between two analogies, right? So you basically learn from something else and apply, and somewhere at a certain moment, even without your participation, your consciousness, your brain makes this comparison, and one event triggers another event. I don't know, you drank coffee and you saw some waves and interference in your mark, and you thought about just interference pattern somewhere else, or you even not interference. So you never actually know what triggered the discovery. So what's really puzzles me now in AI, the use of the pre-trained models. That's how something which was trained on completely different data sets can be used for, I don't know, something trained on the pictures of cats and dogs can be used to describe the quantum states of the molecules. It's beyond my understanding, but somehow those pre-trained models been shown we've been shown to work better, and that's almost magical for me. So so it's just making this analogy between two analogies.
You've touched on a hot topic, that of human creativity, stupidity on the other side. Let me take you up on that, because we have several online questions revolving around this topic, and Vijay put it very nicely. How can we ensure that the use of technology and revolutionary tools in scientific research do not lead to a loss of critical thinking and creativity? Loss of critical thinking through the use of advanced technology. Is this a danger?
I think it was always considered to be a danger, and then I mean, let's be honest, science is not something which we do only now. It's been active for 500 years, and I'm sure that every single generation thought, okay, now science is that. So Newton invented, Leibniz invented the calculus. So everything can be done with it, and then so electromagnetic waves and the four equations of Maxwell. Okay, now we really understand everything. I mean, I'm using the mathematical tools as the example of the tools, but you can say the same about many other tools, and yet it just every time it has been shown that science and nature is by far deeper and by far more interesting, and it's clear that the number of questions which we still have is huge. Frankly speaking, the more I study physics, the more I understand the vastness of this unknown territory. And we already mentioned several times that yes, the technology and tools, they create this global pressure, and they gradually expand this known territory. But this burst, this breakthrough, it happens somewhere in our brain, and only in our brain. So I don't think it will. So the answer is that probably I can imagine some scientists will be satisfied with the little petty work which they do, but the breakthroughs are going to happen, and they're going to happen in human minds.
I think the question is quite interesting because it shows that there is this fear of the technology, and pretty much it's not just now. It always happened. Anything new coming up, there's some people that are a bit afraid, and because they lost control, they don't understand what's going on, and because they don't control, they don't understand what's going on, they want this to be removed. And I think it's possibly the way we react to the unknown. Now, we know, you can bring a child and to any place, he would just catch up the language, he would catch up anything, and we can even keep doing that because the brain is very plastic. So there's no reason to be afraid of the technology, and if we do feel so, I think there is something about the understanding of what's going on that should be threatened. I would be much more afraid of governmental policy, restriction of travel, and restriction of thinking, expressing yourself, than really by the nature of the technology itself as preventing creativity here.
Not being afraid of technology also means that you need to be knowledgeable of this technology to understand the mechanisms of this technology. Aaron, is there anything you could recommend maybe our audience here, mainly young researchers, when it comes to new technologies and maybe being afraid to touch these seemingly complicated tools?
Yeah, we are clearly living in a different generation nowadays compared to my generation. I think that I'm the oldest among the the panelists, and when I started my PhD, there was not even pocket calculators. Only towards the end of my PhD, I bought for myself the first pocket calculator that could tell me that 2 and 2 are 4 and the square root of 9 and sinus of a 30 degrees angle and so on and so forth. And now it's completely different. But I think that the passion of people and the drive of people has still remained. Now we are talking about a new AI program, the chat program that can compose for you anything you like. You know, you want to write a work in your university about the history of the covalent bond, just kick it in. In 2 minutes, you will get a beautiful piece of written work, a study, and so on and so forth. The question is whether it's innovative, and probably it's not innovative. It's more historical, it can compose things, and I think that also proud people, and I think that I am very proud, want to do it on their own. So at the end of the day, the real driven people would not like to rely on such tools. They would like to go to the library to collect the data, but then to think, okay, where the data are leading me? What can I do with them? How can I use them to innovate something, to invent something? And I think that this will be the limitation of the tool. I cannot prophesize that the tools will never evolve to become innovative, but I think that, you know, in our hearts, we are still driven. There is something about us. And there will always be these driven people that would like to do it on their own. And I wish that many of you will be like that rather than to push a button on your keyboard and get something that is ready to go without even reading it and submitting it to your instructor in the university, graduating without knowing even the alphabet, which looks to me like an oxymoron.
I think it actually brings this important thing about collaboration. So that's what I mean, that so technology is important and tools are important. What is important is that you know how to use this tool. So every single tool got a limitation. So, and my first, when I started to do my first PhD, my supervisor always said, so you have to love and know the device which you use, because it's still a tool, it's still a device, and it has many limitations, many boundaries, so each technique got those. So you have to be, so even the best tools, they're not useless, but they're not as efficient if you don't understand how it works. You really need to know it, and it basically means that you have to master the technology, and unfortunately you don't have chance to master all possible technologies in the world. So what is important to have is to have, like what physicists do, is to have a mental model of your system and understand what do you want to study, and then know the possible techniques which would allow you to do it. And of course you are never expert in all of them, so you have to collaborate and work with someone else who can help you to interrogate your system from a different perspective.
Thank you. Didier, your recommendation.
My recommendation?
For the audience, for the students.
Well, I think they should not be afraid of the technology, but I don't think they are. And if they are in this audience, it's because they're very curious and they were very keen to learn. So certainly not be worried about this. What is interesting is to consider themselves as maybe an advocate of technology and understanding how knowledge is critical for the society, how to translate the knowledge into a global scale to the society. And in this audience, we are the future generation of really of promoter or advocate or diplomat of science, and we all have a task. So I really hope that you take this task very seriously, because if you don't do it, who else is going to do it? So that would be my advice.
Wonderful. Now we've been addressing you, the audience, here in the lecture hall, and I'd like to invite you and encourage you to ask questions yourself. You see a few microphones lined up here in the hallway. Please line up, go to a microphone. I will call you if you have a question. And while we have the audience lining up to ask you...
Already aligned.
Already aligned? Okay, then why don't we start with this?
Hi,
Over there, please.
Hi, professors. Thank you very much for the discussion today. So my question is, as my friend used to say, the easy thing has already been done. So the next thing that needs to be done, like the revolutionary science, needs to come from the revolutionary tools. The problem is it leads to the concentration of resources. So yes, if we are in a very prestigious group, the resource is coming naturally. But what is the advice, if you have, for the people who are not as blessed for the resource, that doesn't have the access to those tools that are required to make such revolutionary discovery?
Well, I would say I completely disagree that all the easy things have been done already. So if you look at the history of discoveries, so many of the discoveries which to us now look completely obvious and just how it could be any other ways, they had very, very difficult time to be published and to convince other people. So I don't like this statement that all the easy things have been discovered. They look easy for us now, but at the time of discovery, they look, believe me, they look very, very, very controversial. So Klaus von Klitzing, he's not here, but so he discovered the quantum holofact. So something which is now, I don't know, it's being used in metrology widely, of course, and it's the very basic concept for any condensed matter student. He had terrible time trying to publish his work because no one would believe him. Even now, so today, it's something as basic, I don't know, for any condensed matter physicist as possible. But then, so that's the first statement. But I would say that the lack of tools make you more innovative, probably. So you can really try to trigger your imagination. So. I'm sorry to put my case forward here, but so we started to work on the Gecko tape and on graphene just a few months once we moved to a new lab in the UK in Manchester. So I entered into the lab. So there was nothing there. So there was a turbo pump and a desk and a chair. That's it. So just really completely empty, and it just and believe me, we didn't need our first devices were literally produced by hands only with the stereo microscope. So I don't think. I'm not sure. Okay, I wanted to ask Didier if he says a direct linear proportionality, or I don't know, a square or square root dependence between the price of the tool and the number of discoveries you can make per the unit of time. But I'm not sure if there is such a. So can you plug the log plot?
I think this is a very interesting question because there's really two approaches here. We call that large science, when there's usually very expensive equipment that usually assembled and thought carefully, where there's many people building up. And sometimes this equipment are making something new and they're producing what they expect. But there's also a complete other part of the science, which is exactly what you described, which I would qualify also from the first discovery of exoplanet. At that time, I think the funding was almost none. And we have to do everything with a shoestrings. And there's plenty of examples like that because we're too much ahead. And we're too much ahead of the time, and nobody believed that because it's not yet as part of the streamline of the science. So if you start science and feel that you are not in the right place, don't have the right finding, I think you should ask yourself what exactly you're looking at here. And maybe you're not really looking at complete discovery science. You may be more working more interested about applying elements and developing tools and stuff, which may be a different aspect of it. But the true discovery comes from nowhere at a completely unexpected time, and it should not depend on the money. Money helps. It's always good to have money. But the long list of examples can be produced demonstrating that certainly it was not the trigger of discovery. And when we announced the discovery of the planet, and we had a big problem, and in a way people were reacting, oh, how come such a big discovery has been made but only 2 people? You see this how it works. So sometimes you expect big stuff. We're talking about James Webb Space Telescope. It's a great tool, thousands and thousands of people. Is this equipment going to do a discovery that will lead to a Nobel Prize? Not sure. So maybe it will come from next door.
Very discouraging to the people who run the Webb telescopes.
Yeah, well, and there may be some surprise there, but I think essentially the investment you need to do when you have big money can be predicted to some extent, because that's how you get the money. If you really want to go into unknown territory, the money will just shrink. And the more it's unknown, the more it will shrink.
Thank you very much for this answer. You see, with your questions, you hit a spot here. Absolutely. Thank you for that. Please, we have another question to be asked.
Hi, Professor. I think general relativity is mentioned just in the talk, and it's a typical theoretical physics. And my question is that what do you think about the relationship between theory and experiment? And I think often they have disagreement, like, for example, like some experimental physicists doesn't think, I think string theory is not physics, but just mathematics because no experiment supported. So I want to ask what's your viewpoint about this?
Well, I think there is something that would qualify for anything which we call science. It is not only is physics, it is what we call fact-driven. That's it. So you can come up with any beautiful theory of the world. If there is no any fact that drives the theory and brings the theory, it means nothing. So it's really fact-driven. It's not driven by a book or by somebody, promoting a kind of mental picture of it. It's driven because there are facts. And if you think about the Einstein theory, at some point Einstein was very eager predicting some of the fact that could be checked, and then that made the theory even stronger. And there's still people challenging a theory these days by observing deeper and deeper and better and better. And it qualifies for any field of the science. It's fact-driven. So it's irrelevant, this debate about theory of observation, because the fact is the driving force of science.
So you see, you asked the wrong people. So you've got the bunch of experimentalists who just who are going to screw now badly. So I completely agree. Yeah, if your theory doesn't, so of course theorists would say just if your experiment doesn't fit into my theory, go and measure better. But if we say just if your theory doesn't fit with the facts, probably it's not beautiful enough. So
yeah, never repeat a successful experiment. Absolutely. Right, Aaron.
Well, I think I cannot compare biology to physics. I think that the physicists are kind of aiming more at the unifying theory. In biology, there is no unifying theory, so biology is much more eclectic. Some people work on viruses, some people work on the brain. There is nothing between the brain and viruses, except for basic elements like DNA and RNA. But otherwise, the mode of action are completely different. Some work on plants, some work on symbiosis. It's completely eclectic. And at the end of the day, biology is so complicated that you need at the end to experiment it in a wet way. If you are developing a drug, at the end the target is the human being. And I don't know that there are not two human beings that walk on the face of the planet that are identical, not even identical twins, because they are different epigenetically, because they acquire different methylation of their RNA, of the DNA, and so on and so forth. So the response of one person is not the response of other. Maybe one day will come and we'll have so much information that we'll be able to predict a priori that with your genetic repertoire, the drug will do that and that. Until then, we need to experiment it and just wait for the result. So I think that in biology there is much less place for a theory, and at the end you have to go to the think to turn on the faucet, wetten your hands, and do it wet-wise.
Thank you very much.
Okay, thank you
I
so
suggest
much.
we continue on this side and then over there.
Thank you. With your many years of experience in science, I was mostly wondering how you feel about tools that allow collaboration, which we've recently seen with Zoom and online meetings, online conferences. Do you think this will change the way we do science or the way we collaborate going into the future? Or maybe with your 40, 50, 60 years of experience, how would you say that these tools have changed the way you're doing science from when you started to how you're doing it now?
Thank you.
Oh, I guess.
Well, I can start easily. I mean, the web was created by the physicists that needed to exchange data. And we've been the first to use the email way before it became into the public. So science is about communications because you need to exchange, to challenge your ideas, and you need to communicate. So anything that enhances the communication is good. It does not magical because it doesn't make the communication, but it enables the communication. So great, I think I'm a great user of Zoom communication, any kind of tool like that.
Me as well, but I still way prefer the in-person meeting. On the blackboard, I don't know what's the magic the blackboard got, but it's so much, you just manage to go through so many more models within shorter period of time. So if I would definitely always prefer in person. And I mean, come on, you cannot, you can just call in person an idiot on Zoom doesn't have exactly the same connotation as calling person an idiot in real life, right?
Does this answer your question?
Yes, yes.
Thank you very much.
It's also, has it changed the way you're doing science, or do you think it will change the way we're doing science?
Only we knew how the science is done. So the science is done in your brain, and then what triggers it, we have no idea. I mean, at least I have no idea.
Well, we wouldn't have such a discussion on Zoom, I guess. Okay, thanks very much. Next question over there.
Yes, hello,
Please.
thank you. So you've talked about, let's say, the capacity of the brain and how unique the brain is in generating ideas and drawing analogies. So one thing that puzzles me is, let's say, the amount of information that we can process. I mean, I think in let's say, publishing in science, I think in the, let's say, since the 2000s, the number of papers that has been published is higher than all the papers that were published until the year 2000. So I feel that, let's say, I mean, we still generate ideas in the brain of a single human being or maybe in a collaboration, but do you see, let's say, the amount of information that we generate? I mean, let's say there's of course a benefit in it, but I guess it's also a challenge, let's say, in the way we do science, that as a single scientist, we can only process a limited amount of information to generate new ideas. So I see it, personally, I see it as a challenge because I feel bombarded by information all the time. So how do you see it on a personal level, and maybe does that require new tools that kind of pre-filter information, or does it change the way we do science on the long run?
I'm not an information scientist. I'm sure someone with the right background will be able to give you more proper answer. But here is my amateur approach to it. So I would say that probably when our brain fills up, we just die. So that's why we live so short. So things like trees, they don't need to bother to process information and fill up their brain that they can live for thousands of years. So, but then you're right. So the amount of information gets larger and larger and larger, and that's where the physics approach help, where we create a model where we just digest and dissect the system into some basic parts, and then we just and then the model is basically archiving all this all those data into the digestible form. And then once the model is created, there is even better way to archive this information. We create a new language. So I mean, if you I don't know. So just we talk about sorry to get into my territories. If you go into the condensed matter physics, we talk about electrons, you talk about holes, even though none exist. So it's some excitations in there. So in the Fermi sea or whatever. So, but then we just learned how to we create a new language, a new operator, a new mathematics, and then it's becoming way more compact. And if you look how we manage to compact our data over time, so the growth of knowledge is not exponential, so it's actually quite slow in that respect.
Thanks very much. I suggest, in light of time, we go straight to the next question over there, please.
Hello. So I have a question regarding interdisciplinary research and the creation of new fields. Like, for example, these days, if you do research, start doing research, you have a lot of data over the internet and you have a lot of fields, and every day there's a new paper on every different topic. And so I wanted to ask you because these days we all have, not all, but most of the people have primitive mindsets, and it's very difficult to create a new field. To create a new field is very difficult. What tools do we need? And for example, let's say cancer. It's a very big topic. Every day we have a new paper on cancer. But what would it take to answer that question, to solve the puzzle? Will it take a new tool, a new field? What would it take to answer that question? And the main question is the creation of a new field from current disciplines.
Sorry.
I don't know why you have to generate a new field. You talked about cancer, didn't you? So I can bring you a zillion of questions about cancer that are still not answered yet. For example, why cancer of the skin is so easy to treat, while pancreatic cancer is so resistant to every chemotherapy. The same for ovarian cancer. What's going on in these different tumors that are making them different from other tumors? So there are so many open questions, even within, the big definition of a disease, that are still completely available for investigation. Why do you need to open a new field?
So you mean that creating a new field is not sufficient to answer all
the questions? The question is, what is a new field? You can invent a new chemotherapy, a new class of drugs, I can bring you many examples of new drugs that are entering. Cancer therapy, for example, moved from chemotherapy now to biologics. We are using antibodies which are very specific, like Herceptin and others that are targeting very specific molecules and have much less side effects than the chemotherapy that is non-specific. So here you have a new field within an already known field. So I think that, there are always new questions that are coming up. You don't have to bother yourself with something, well beyond your ability or something that you have to prophesize. I think that there are so many open questions. Think about Alzheimer's disease. Think about all the neurodegenerative diseases. What's going on? We have no clue what's going on, but even the slightest clue. We don't understand memory. Think about these diseases. You are losing memory, right? So it's already known disease, Alzheimer's disease, and people are losing memory. What is a memory? That I tell you your mother, so all of a sudden pictures are coming into your mind. Smells of food, of ceremonies at home. Where do they come from and why they get lost? What happens? What is the connection between aggregated proteins and memory? I mean, there are so many open questions in already, I wouldn't say known field, in known entities that we are starting only now to unravel, that I won't be bothered at all. I would not be bothered at all.
Okay, I would like to push in this direction even a bit further. I think science is very organic in the way it's being built, and look at the double helix of the DNA when Crick and Watson, as a physicist, playing with the equipment of physics in the physics lab. Well, in a way you can say they created a new field, but actually this is just what they found was so interesting that it attracted a lot of scientists, and things will be very organic. So there is a little bit maybe of a point behind your questions. Is not about the science, it's about the curriculum that drives the science, because it happens that the way we organize institutions and also the funding agencies is organized into field. And that's maybe what you are, alluding on here, practically. And I think this is a mistake of the institutions that date from maybe the Victorian age, when we start to define fields in science, I think the science is not anymore so easily identified as field. And it's up to the institutions to adapt to these situations and to enable, I think, a culture that would be much more agile in the way it is being done. And that's why you see popping up in different places what we call cross-disciplinary centers or joint activities to try to remedy to this lack of creativity as part of the curriculum, the way it's being done. But setting up a curriculum that would be more open is complicated by design, because then how do you assess it, and how do you deal with a funding agency when you start doing something which is in between different kind of disciplines, and how do you assess that? So it's certainly not a scientific, element, because scientists can move from one element to another one and doesn't care about the field. It's how the society and how the practical structure of the governance of the science is going to reflect on that. That is really what you're talking about, unfortunately. And that is what us as a scientist are battling again quite often. Unfortunately, we're quite too much sometimes fighting wars because people, they don't understand how organic is science.
I wanted to echo Didier, so just 10 seconds. So you are educated as a biologist, chemist, physicist. The moment you graduate from your university, you shouldn't be allowed to call yourself a physicist or biologist. You are a scientist. You cannot just put the shores and then say, okay, I'm using this knowledge and I'm working within this field. You are a scientist, and science is global. Is the same physical laws which are operational in biology or in astrophysics. But again. It is true that we are educated as within a particular field, and maybe so now we try to mix and match different disciplines together. And there are universities like this which don't teach physics. They teach quantum, which is mathematics plus physics, or they teach material science, which is physics plus chemistry, and so on.
That was longer than 10 seconds. Thank you for this answer. Quick question, quick answer.
I try to be quick. Thanks a lot for a very interesting discussion. My question is, recently FDA just pushed forward the idea of some medicine may not need any more testing. So this is an example of how science policy can affect how we do science. Can you comment more on this, and what could be the challenges? What could be the challenges, and also whether it's one of the ways to drive forward the innovation of new technology, new tools? Yeah. Thank you.
What was the question? I didn't get it. Can you repeat it?
Please rephrase your question. You had two questions in there.
Yeah.
So the first question is basically it's just one question. How do you comment on science policy? Something like for example, FDA just pushed forward the idea of some medicine may not need animal testing. For example, in biotechnology, we use a lot of animal testing, like animal models. But this kind of policy, do you think is really, in the future, could change how we do science in general? We need to think about alternative methods, new technology, new way of proving the hypothesis. So, yeah, I just want to hear what you think about this changing in the future.
Thank you very much.
Can you get rid of the animal testing altogether? And what
I cannot. Work? Yeah, okay. The FDA just 2 weeks ago issued an instructions or a new law. It depends on how you look at it. That in the future they will approve drugs without animal experiments. But this is a little bit too far. So they opened the door to this one, and I mentioned in my brief talk, in one of the brief statement that I gave here, that we are moving now to organoids, to tissues on chips, which might replace the animals. What we'll need is several drugs that are using the two methods, and we need to correlate, because animal experiments are okay, they are not ultimate. You know, most of the experiment, you know, how many mice were cured from cancer and how many drugs are failing in phase 3 clinical trials. I mean, it's easy to cure a mouse. It's very difficult to cure a human being. And most of the experiments fail at the human clinical trials at phase 3. But animals are still a whole organism. They have heart and blood and lungs, so you can monitor a lot of parameters. But people are moving from it, and for the new drugs that are coming, people will have to compare the two and to convince the FDA that these are parallel or even the organoids have an advantage over the animal, and then gradually, hopefully, the animals will phase out. More importantly, we are talking about clinical trials in human beings because I'll be able to take tissue from human, just to take a blood, and to make different tissues out of it, to convert it to stem cells, and then to take the stem cells and to convert them into the different, and I will be able to circumvent even clinical trials. This is a little bit of a far-fetched dream, but that might also happen. So it will save, again, a lot of time, a lot of money, and a lot of suffering, because there is an ethical issue with clinical trials. Because in clinical trials, you always have two groups. One group that enjoys the new drug, if it's successful, and one group that gets the old one and might suffer the disadvantages of the old drug. So there are also ethical issues in clinical trials. So I think that the world is moving for them, and I think that the step of the FDA was crucial in that respect.
Thank you.
Thank you very much. Thank you very much all for asking such wonderful questions. And time is up, I have to say. Dear friends, we only just started a fantastic discussion that led us from classic tools to far-fetched dreams. I thank the panelists very much for sharing their thoughts. I very much enjoyed your comments and contributions to this GYSS panel, and I thank the audience, all of you, for attending and staying true on the path of science. Thank you very much.